Hi, my name's Paul McClellan. I'm the editor of Breakfast Bytes, which is a blog that comes out every day on the Cadence website. And I'll come back to that right at the end, since if you really want to know what's going on in the industry and keep up with it, then I think this is a great resource. So today I'm going to talk about Semiconductor 101, so a very basic introduction to semiconductors. This is not going to go into a huge amount of details. We're not going to look at how transistors are constructed or anything like that. We're going to look at why semiconductors are important and how they've been changing over the years, the economics, how they're built, and in particular how they're designed, which is where Cadence comes in, of course. So we have this intelligent system design strategy. I'll come back to this at the end when you've got a bit more context to understand it. Some of you may understand this all already, others may be struggling a little bit until I've explained everything in the middle part of the presentation. But across the top are the main industries where semiconductors are heavily used. Consumer, it's everything from smart doorbells to wireless routers and so forth. Hyperscale is big data centers, especially cloud data centers, people like AWS and Google. Mobile is smartphones, of course. Communications is 5G, wireless base stations, silicon photonics inside data centers and so forth. Automotive is obviously cars, but increasingly it's focused on advanced driver assistance systems, which have a lot of complex silicon in them, as opposed to traditional automotive from a decade ago, where it was all essentially very simple designs done on old processes. Aerospace and defense is obviously, planes and tanks and things like that. Industrial is mostly robots, but there are other things you can put under that. And then health is everything from things like heart pacemakers to the equipment that hospitals make use of. So I said Cadence is sort of in the EDA business, and EDA, the first question to answer really is, I guess, what EDA stands for. We're actually in the EDA and IP businesses. So EDA stands for Electronic Design Automation, which I think is somewhat self-explanatory. It's software that designers use to design chips. Intellectual property is a bit of a confusing term because it sounds like it might be something to do with patents, but it's nothing to do with patents, although, of course, Cadence does have patents as well. It's small pieces of chips, so like Lego blocks, essentially, for designers to use, so they don't need to design them themselves, because in the olden days, 40, 50 years ago, people designed absolutely everything, so it was like having to design your own Lego blocks before you started to put them together. Today, we have things like standard cell libraries, so IP goes from simple things like that all the way up to complete microprocessors and perhaps even more. There are two main parts to EDA, to Electronic Design Automation. One is the design of integrated circuits, which are semiconductor chips, and the other is PCB, which is printed circuit boards. So almost every chip goes on a printed circuit board. But as a part of the industry and as the sort of focus as to what's driving the electronics business, integrated circuits and semiconductors in general are the more important part. Although increasingly advanced packaging, as we'll see later, comes into play much more significantly these days than even 5 years ago. So let's take a little bit of a look at semiconductor economics, because this is the thing that has driven electronics for the last 20 or 30 years. So I'm sure you've heard of Moore's Law. It shows up in the general press and in places like The Economist, Business Week. That's the number of transistors in a chip will exponentially double every 24 months. And this picture on the right is to some extent a bit of a joke, but it's also got a serious point, which is this is not something that only started with the integrated circuit. The designs have been getting smaller and getting faster for many years, many decades, and I don't know quite what era this goes back to, but the 40s and 50s, I'm guessing. So Moore's Law, the original graph Moore produced is there on the left. He actually only had 4 data points. So it was a bit of a gutsy move to say that this was going to go on. And he certainly at the time didn't believe it was going to go on for 50 years since he wrote that piece in Electronics magazine. But it has, pretty much. And you see that over on the right, where you see a range of microprocessors, mostly Intel, but not only Intel, from the 70s up to quite recently. And you'll see they're all on a straight line, but you actually have to look more closely and see that on the left-hand side, where the transistors per chip, and it's a logarithmic scale. See, at the bottom it's 1,000, and at the top it's 1 billion. So it's worth remembering that it actually is exponential. And exponential tends to mean that it goes along very flat, nothing much seems to be happening, and then it goes literally vertically, or almost literally vertically. So you can see here, this is actually a photograph from the Computer History Museum of Moore's Law with, you probably can't see in the picture, but with various microprocessors in the same way as they were shown on the previous slide, where it was a straight line with a logarithmic scale. This has a linear scale, and so you actually get to see the exponential effect. The density of transistors, as a result, has gone up significantly. If we just go back to 2008, so 15 years ago or so, we had a process, I'll explain what this means in a moment, called 45 nanometer. We had 3.3 million transistors per square millimeter. In 10 nanometer, it was up to 100 million transistors per square millimeter. Now the most advanced chips are 5 nanometer, and they run more like 250 million transistors per square millimeter. But I actually like to look at this as what I call inverse Moore's law, because this has been what's really driving the semiconductor and the electronics industries, and indirectly the EDA industry, which is, instead of just sort of saying, oh, the number of transistors on a chip doubles every couple of years, the cost of implementing any functionality in silicon halves every couple of years, which means it drops by a factor of 30 in 10 years and a factor of 1,000 in 20 years. And so when you look at it on a 25-year time scale, something that cost $1 million 25 years ago becomes $200. When I started in this business, one of the investors in VLSI Technology, the company I worked at the time, was Evans and Sutherland, and they made multi-million-dollar military flight simulators. But now you can buy a video game console for like $250, or even your kids can buy one for $250. And the performance is much better, and the graphics is much better, and it doesn't cost you $20 million. So on the left, you see what a 1980s flight simulator looked like, what you got for your $20 million. That in some cases, they actually had all the hydraulics that moves you around, like in a ride at Disneyland. Star Tours at Disneyland is a giant flight simulator. Then on the right, a $500 iPad with better graphics. But really, Moore's law, in that sense, has come to an end, and the future isn't going to be quite the same. If we look at the iPhone as a good example that everybody's familiar with, the first iPhone over on the left was $349 and up. The current iPhones are about $1,000 and up, depending on how much memory you put in them, whether you buy the Pro model or not. But what's not going to happen, you're getting a lot more functionality, but it's costing you more. And what's not going to happen is that $999 is never going to suddenly drop to be $5 in the same way as happened with, say, electronic calculators that dropped from something that were relatively expensive to little credit card size things you'd give away at trade shows. So to manufacture chips, the chips themselves are fairly cheap because you build a lot of them, but the factories to build them are not. So we actually build them in something called the semiconductor process, and there are lots of different ones of those depending on what generation of process, and each factory has to be built to build a particular generation. So we used to measure these in microns, which are millionths of a meter or thousandth of a millimeter. So when I started, it was 3 micron. We went down to about 0.35 microns, still calling them microns, and they're the length of the transistor on the silicon. Now we measure them in nanometers, written nm. So once we got down to about 135 0.135 microns, we started calling them 135 nanometer, and then that now more recently is 28, 16, 7.5, coming up in the future, or in 2022 is 3 nanometer. But there's nothing 7 nanometer on a 7 nanometer chip. These are really just numbers today. The transistors are kind of folded up in a way they didn't used to be, so they don't actually have a length in quite the same way. After 3 nanometer, we probably have 1.5 nanometer. Intel has started calling these, measuring these processes in angstrom units, which is 10 to the minus 10 meters. So maybe we were in the micron era, then the nanometer era, and we're coming up to the angstrom era. The wafers themselves, we don't build one chip at a time. We build them on a big wafer, which is the size of a dinner plate, so 300 millimeters, 1 foot, or the older generation was 200 millimeter, which is 8 inches. So it's like a side plate versus a dinner plate. There was an expectation we'd have 450 nanometer, 18 inch, and some experimental work got done in that era. Here's me actually holding one of these 450 millimeter wafers, but they're not going to be coming anytime soon, and possibly never, just because the equipment is going to be so expensive to re-equip a fab to use 450 millimeter, and it's not clear the productivity gain will justify the investment in the equipment. So what does a fab look like? Here's a fab. This is TSMC's Tainan site in southern Taiwan. So I think the first thing that you can see is that it's huge. It's a bit like looking at an airplane or an automotive assembly plant. They're on the same kind of scale, and definitely a similar kind of price point, or actually more expensive probably. And inside they look like this. There's just lots of equipment. Over the top, you can see those sort of tracks that look like sort of upside down railway. Those move the wafers around from piece of equipment to piece of equipment. But I think the most obvious thing in this picture is there are no people. Basically, the people that control all of this sit outside of the fab. The fab is incredibly clean. An operating theater in a hospital is significantly dirtier than a fab. We can never manufacture semiconductors in a hospital operating theater. And of course, occasionally people have to go in there and do equipment maintenance, but for day-to-day operation, people are not in the fab. So a modern fab is very expensive. It costs $10 to $20 billion. It has a capacity of something like 50,000 to 80,000 12-inch wafer starts per month, which is how we measure the capacity of a fab. Every couple of minutes, a new wafer starts, and that, if you multiply that all up, you get to 50 to 80,000 wafers in a month. The cost means that it depreciates. If you depreciate it over 5 years or something reasonable, it depreciates at about $200 a second. And so that means it needs about $1,000 worth of business per second to justify owning a fab. And everybody up until maybe 1990, everybody, or even later, everybody owned their own fabs. Every semiconductor manufacturer owned their own fabs. In fact, in 1999, I think it was, Jerry Sanders, the CEO of AMD at the time, was famous for this thing, Real Men Have Fabs. This was in an era when the top number one selling book on the charts for books was a book called, I think, Real Men Don't Eat Quiche. Funnily enough, it turned out that AMD were the first company to sell their fab, their manufacturing, and they created one of the fabs called Global Foundries. And it also turned out that they were the first major semiconductor company with a female CEO, so, real women don't have fabs, I guess. And today, when you get to the leading edge, there are just 3 leading edge non-memory manufacturers. They're Intel, which is what we call an IDM, an integrated device manufacturer. They both do their manufacturing, they do their design, they manufacture it themselves, they sell it themselves. And under their newish CEO, Pat Gelsinger, they're getting heavily into the foundry business as well, but it's sort of too soon to tell how that's going to go, because this is literally in the last 6 months. TSMC in Taiwan Semiconductor Manufacturing Corporation, That's a pure play foundry. Pure play means they don't design any chips themselves. They don't market any chips themselves. They just develop the process. They build the factories. They build the chips. Samsung in Korea, and they have a fab in Austin as well, is both an integrated device manufacturer and a foundry. They build chips for other people in Samsung Foundry, and they build chips for themselves and then put them in phones and TVs that they then sell under the Samsung brand name too. In DRAM, in memory, we have DRAM and flash, the two main memory technologies. In DRAM, there are really three manufacturers of significance: SK Hynix, Samsung, and Micron. And in flash, Samsung, Toshiba, Western Digital, Micron, SK Hynix, and Intel. So there's flashes that are, in a way, a lot more competitive. All the other semiconductor companies that you've probably heard of, Qualcomm, Broadcom, NVIDIA, are either fabless. Qualcomm, Broadcom, and NVIDIA have never had a fab, or they're what's called fab-lite, where they used to have their own fabs, and now for the most advanced processes, they go to a company like TSMC or Samsung, but for those older processes, they still manufacture themselves in their old fabs, ST Microelectronics being another one there. I actually wrote a book on this along with Daniel Nenny, so if you want to dive deeper into how this transition from what we just called semiconductor companies, but now called IDMs, took place to the situation we have today with fabless semiconductors and foundries being the primary way that chips are built, then you can buy this book, or if you send me an email, I can send you a PDF of it, or you can just buy it on Amazon for, I think it's $10. So finally, let's get to design and how chips are designed and where Cadence fits in all of that. So first, let me point out that chip design is not like any other design, really. The nearest I can come up with is that it's like having to design the Airbus 380, but you only have 12 months to do it, and you're using manufacturing technology that's never been used before, and you're using new software development tools that have only just been released and have never been used for real design. And then you have to put the first prototype straight into high-volume production in August for the Christmas market, and then work on the next, even bigger one, since that design will be obsolete by the following summer, and you'll need a new one for the following Christmas market. And this is really, if you look at what a smartphone manufacturer does, they do this once or twice a year. They come out with completely new, incredibly complex chips, and they expect them to work first time. And as a result, for Cadence, our R&D expenses are actually 40% of our revenue. We have, as you can see on here, we have, I think, probably closer to 6,000 R&D engineers these days, a couple of thousand field engineers, lots of patents, and we develop stuff all over the world. We have 23 global development centers for creating software in obviously in China and India, but also Brazil and Israel, and of course in the US. So here's how chips are designed. So this is maybe the most important slide in the whole presentation. If you kind of internalize this, then other things you can slot in to this framework. So you have an idea, and you want to build a chip. And the way you actually do that is you have to express your idea in this language called System Verilog. And then there's a process called functional verification, which allows you to check whether the System Verilog you wrote is what you wanted it to do. So it's a bit like writing software, where you want to check that the software actually does what you planned it to do. So that's kind of equivalent in a way to compiling and running your software, but because this is chip design, we can't actually build the chip and then check whether the chip does what we want. We have to do it all in a simulated environment on workstations. The next stage is synthesis, which takes that System Verilog and creates a sort of what we call a net list, like a interconnected network of like the little tiny Lego bricks that go to make up the design. And then that goes through physical design, which basically turns all of that into what will actually go to the foundry to manufacture initially the masks, and then the masks are used to actually manufacture the wafers. IP slots in at two places. One, synthesis, where we have some IP that's so-called synthesizable, it's in the Lego bricks already, and some which is more at the physical design stage for analog design in particular, where it's already been reduced to what needs to go on the silicon. And the problem with the physical design version is it has to be different for every process, so it's a lot more expensive, whereas the synthesizable one can be taken through the automatic process to create it. We also bring custom blocks in at that point. If there are things like analog in particular, RF, those come in here, then in general not synthesizable. Then we go through a process called sign-off, which is really to check that if we build the chip, it will work. And when we're happy that everything is working, we create what's called GDS2, which is literally what's going to go to the foundry to build this. We do physical verification on that GDS2 to make sure that that has no problems, so that the foundry will be able to build it. This is a sort of joint effort where Cadence provides the physical verification tools, or in general the EDA industry, and the foundry provides the rules that have to be checked against to make sure that if they build it, then it will work. And then the final stage is called tape out. Of course, these days it doesn't involve any tapes, but 40, 50 years ago, it literally involved writing out the design onto a tape. And the tape would be FedExed to the foundry, or if it was an IDM, would be taken to where the masks were going to be made. So we have a lot of products in all of these spaces. I don't expect you to remember all of these, but you may hear them later. So functional verification, we have Excellium, which is our simulator, Palladium, which is a high-speed emulator. That's a great hardware, $1 million piece of hardware. Protium, which is FPGA prototyping, and Jasper Gold, which is formal verification. So some of these I'll come back to a little bit later. Our synthesis product is called Genus. Custom block design is done with Virtuoso for layout, Spectre for simulation. Digital physical design is done through Innovus. Sign-off, we have a whole portfolio of tools, Tempus for timing, Voltus for analyzing voltage drop, Quantus for extraction, Modus for doing test generation. And then the physical verification tool is called Pegasus. And as a general rule, our digital flow products end in US, and our simulation products end in UM, but there are a few exceptions, as you can see. And then the PCB and IP tools. Well, the PCB tools are called Allegro for doing the layout, Sigrity for signal integrity analysis, OrCAD, which is a lower-end PCB tool for the mass market, as it were. And then in IP, these are not tools, these are the building blocks. We have Tensilica processors, Denali memory, IP, PCI Express, and USB. All of those little sockets that are on the side of your computer, they typically have some piece of IP behind them on the silicon that when you plug the cable in, the cable talks to the Ethernet, or another obvious one. So as I said, chip design is not like other design. The physics is constantly changing. Design tools are inevitably somewhat untested for the most advanced nodes because there are no designs for us to test them on until we produce the tools. And then once we produce the tools, people try and produce designs, and that breaks them. So it's a sort of iterative process. Over time, what people care about keeps changing. In the 80s, it was mostly area, which is cost. In the 90s, it was much more focused on timing as well as area. In the 2000s, power, timing and area. Power became very important when it was obvious that we couldn't keep increasing microprocessor clock rates much beyond 3-4 gigahertz without the chips getting so hot they were going to melt. And now it's really everything at once. The design cycle is pretty unforgiving because they're often focused on things like Christmas and the Chinese New Year, which aren't going to move no matter how much you might want them to. So you really either get your chip working in time, or you're going to miss that part of the, the market, and will be a lot less profitable. It's a huge scale. There are literally several billion active parts on one of these chips. And it's also very expensive. You need a huge team to do the design. For a typical state-of-the-art chip, it's somewhere like 10 to 100 million, depending on how much we use. A state-of-the-art microprocessor is probably $1 billion. And it's not really just for semiconductors anymore. If you think about 10, certainly 20 years ago, almost all semiconductors were designed by semiconductor companies, people like Intel and Texas Instruments and ST Microelectronics. But increasingly, semiconductors are designed by the system companies who are designing their own chips. So Google, Amazon, Microsoft, Facebook, none of these are semiconductor companies. Alibaba, Tencent, Baidu, Tesla, all of these people design their own chips because otherwise they don't have any differentiation because they're just left using the same products as their competition. And it allows them to provide lots of special features that make their chip different from other people's chips, which is kind of obvious in the case of, say, Apple or Tesla. Here's an example just to show you the scale of these things. This is the AMD Radeon VII, I think that's the way they pronounce it. This is not even their current generation. This is like a year ago's generation. It's 19.2 billion transistors. But when that was designed, it was designed in about 2 years. And that works out to be 25 million transistors per day. And when I started in this business, back in the early 80s, 10,000 gates, which is like 40,000 transistors, was the biggest design we could do, and it would take a year to do it. So that's now something that gets done in a few seconds. And just to compare, the largest commercial airliners have 3 million parts, and that's including every single rivet. Not just the sort of big obvious things like the engines and the flight surfaces. This shows the cost of design, how it's been going up over the last years, although it's actually done in process generations. If you look at the bottom, it's by process generation. One thing you'll see is that sort of pink-colored block has been getting much larger. That's software, so increasingly a lot of software goes into these chips in the sense that the system has software plus the chip, and the chip's kind of worthless without the software up and running. Another difference is planes have to fly eventually, whereas chips are expected to work first time. Certainly in the commercial world, chips mostly work first time. And as a result, the bulk of design time is and the investment is in risk management because the plane has to fly. And so you have to guarantee it's going to fly. It's going to cost you literally tens of millions of dollars to tape it out and manufacture it, and it will take about 5 months. And so you're not going to do that until you're really certain that it's going to work, which means not just that the chip has to be correct, but you have to make sure that the software will run on the chip as well. And you can't really back off too much from the absolute state of the art that you can do with the process. Otherwise, you're investing in a big new fab and then doing a design you could have done in the previous fab. So as a result, something like 2/3 to 3/4 of the design cost is one form or another of verification. So let's look at systems. So going up one level really from chips. So chips go on boards. This is actually a board from inside our Palladium emulator. So you can see the big squares, silver squares, which are the main chips, and then there are obviously other chips on there too. Yeah, but increasingly, because Moore's law is kind of running out of steam, designs are getting too big. Designs don't yield very well when they're very big. So increasingly, we're putting systems into complex packages. The catchy word for this is more than more, because instead of just going for linear scaling, we're going for scaling in the third dimension typically. And this is really a quite dramatic change that's taken place over the last 2 or 3 years. More and more chips are just developed using these technologies, and the foundries are all providing packaging technology that enables them at an economic cost. Obviously, at some point, if it costs too much to build it this way, then with the more approach, you'll do it the other way. So the cost has had to come down as they've had experience primarily, in at least in the first place, with mobile and to some extent with microprocessors for data centers. But systems contain software, as I said, a lot of software. There's supposedly 25 million lines of code in an F-35, 100 million lines of code in an ADAS-equipped car, or a self-driving car, for sure. So that's ADAS is things like intelligent cruise control, where with radar it knows how close the car in front is, automatic emergency braking, traffic sign recognition. If you've driven a car where it shows the speed limit on your dashboard, that's traffic sign recognition. And it's moving towards autonomy or self-driving. But you can't really boot an operating system in a simulator. So you need to use something like this box here, which is a Palladium emulator. And here's, on the left is the Palladium Z2, our latest emulator we announced in about April. And on the right, the Protium X2, which is an FPGA prototyping system. That's faster than the emulator, but for hardware debug, it's much more unwieldy because it takes a lot longer to compile because there's an FPGA place and route involved. But basically, nobody's going to tape out a chip until they booted the operating system and tested at least a lot of the software. If you're NVIDIA, you test that various games actually run correctly on your emulated GPU. So let's look a little bit at the markets for software, for semiconductor. So the biggest market is mobile, smartphones, and I like to sort of try and date these things to an absolute event. And so the world changed in smartphones on the morning of January the 9th, 2007, when a Starbucks barista received a call for 2,000 lattes to go. And it was the first non-test call on an iPhone. And Steve Jobs, you can watch the keynote on YouTube. He calls Starbucks from the stage of the Yerba Buena Center for the Arts stage. As you can see, since the iPhone was announced in 2007. This chart starts at 2008, and you see it grew really, really fast. Now it's flattened off. It's still the biggest market, but it's not going to grow at 40% anymore because basically everybody already has a smartphone. So it's more of a replacement market. And there are approximately 1.5 billion smartphones shipped per year. So you can work that out and divide it down to how many ship per minute or something, and it's still quite a big number. Automotive is the next biggest market. I mentioned this earlier, that old automotive was low complexity, 8-bit microcontrollers. It was all about reliability and cost, and they didn't do anything anywhere near any leading edge process. But now the capabilities required for ADAS and autonomous vehicles mean they have to use advanced processes, but with automotive reliability. So it's been a learning exercise for everybody because the automotive people don't know how to do design in advanced processes, and the foundries haven't until recently had the experience of delivering automotive reliability in advanced processes. As a round number, there are about 100 million vehicles per year built in the world. Actually, right now, not, because they can't get enough semiconductors, but in a normal year, pre-pandemic, it's about 100 million. Aerospace used to be the big driver of the semiconductor industry in the 60s and 70s. Production volumes are very small because you don't buy that many fighter jets or satellites or pretty much anything. Maybe if you put a chip in shell or something, then every shell, the numbers get a bit larger. But in general, when you start looking at the number of units and you're measuring the units in planes or satellites, the numbers are pretty small. In fact, one of the DARPA program managers at a keynote I saw him give said that he'd worked for Texas Instruments in the mobile industry, and he said he's never seen a DoD production volume that is more than the chips they give away as samples in the commercial world. High performance computing is another big, this is just driven especially by cloud data centers that uses a lot of the highest performance processors. It uses a lot of routers. It's a lot of optical stuff of one form or another, because it's all done with, well, not all, but a lot of the communication is done with optical networking these days. One particular area of importance is deep learning training. Increasingly, as we move towards more and more artificial intelligence, training is done in cloud data centers. NVIDIA is leading. AMD is growing. Google has their own chip for this called the TPU, the Tensor Processing Unit. And so do some of the Chinese hyperscalers like Alibaba. Next is the Internet of Things. So firstly, cars and mobile phones are not counted as things, although obviously a car and a mobile phone is a thing. But they have their own market, so we don't include them in here. One challenge is it's very fragmented, whereas, as I showed you earlier, semiconductor is a mass production business. If you're not careful, you only need 3 12-inch wafers to do your entire production volume. The biggest part of the market, I think, at least for now, is industrial IoT, things like predictive maintenance, which have a clear ROI. Consumer IoT is less clear because it's not really clear how you can make a lot of money on $1 chips or $2 chips. We have smart everything, smart cities, smart factories, smart farms. When it has smart in it, that means lots of IoT. A lot of voice involved in it, Alexa, Google Home, Apple Siri, for example, and increasingly inference at the edge. So I said the AI training is done in the data centers, but in general, a lot of the AI inference, which is actually using the models, is done at the edge. And the Tensilica processors that I mentioned earlier are used heavily for that. It's, as I said, it's fragmented, very. Here's a chart I don't expect you to be able to read or even sort of see what the blocks are, but it's just to give you an idea of how many companies are involved in IoT. And this is a couple of years ago, 2019, so I suspect that the chart will be more complicated now if somebody tried to put something together. So let's go back to intelligent system design. This is the slide that we came in on. And intelligent system design breaks down into 3 areas. So design excellence, which is what Cadence has been doing for the last 30 years. Custom IC design and simulation. Digital IC design and sign-off. Functional verification, checking how System Verilog does what it's meant to. And then the IP, intellectual property, things like Tensilica processors, but also all of these interface IP as well. At system innovation, we're looking at PCB, advanced packaging, and we have a lot of analysis tools for both thermal and electrical analysis of these systems that scales up to huge numbers of servers in the cloud so that we can get results in a reasonable length of time, even on the most complex systems. And then pervasive intelligence, which we used to mean 2 different things. One is using machine learning technology ourselves. Cadence has machine learning technology inside some of our tools. And then enabling artificial intelligence for our customers. Across the top, you see those market segments that we just went through in a little bit more detail. So let me put in a plug for what I do. So this is Breakfast Bytes. It's a daily blog on the industry, not just about Cadence, but the whole industry. It comes out on the Cadence website every day. It looks a bit like on the right-hand side here. The easiest way to remember where it is breakfastbytes.com, but you can always find it on the Cadence website anyway. And what I recommend you do if you're interested is subscribe to Sunday Brunch. I put out an email that goes out on Sunday night every week, which lists the posts from Breakfast Bytes from the previous week with the first 4 or 5 lines, the title, and one of the images, so you can see whether you're interested in it. And if you are, it's just one click and you can be reading it. And every post looks like this at the end, where it has this sign me up button. So if you click on that, it'll take you to a page where you can type in your email and sign up to get Sunday Brunch. As I said, it comes out on Monday morning for all intents and purposes. It comes out Sunday night, which is a funny time to have brunch, but It's a good name. And that's it. So, Semiconductor 101.